the black hole, it has a vacuum. I mean, when you find this partial solution, for example, it has mass, charge, and momentum. Okay, with these three numbers, you can define the vacuum solution. But there are many possibilities. Internally, the black hole can be configured, can distribute information in many different ways, proportional to the entropy, actually. The entropy, which is proportional to the event horizon, to the area of the event horizon. Still, even if you change the configuration many different ways, still you will obtain the same mass, the same charge, the same angular momentum. But the spectrum Hawking appears is when the black hole selects, due to, in this case, there should be external perturbation, maybe, who knows, the expansion of the unit, whatever. But it selects one ground state. And this is where this spectrum appears. This is the interpretation. I mean, if we follow literally the dictionary of spontaneous symmetry, and this is what it should happen. Then and the process repeats again and repeats again and repeats again. Why it could be connected with the information paradox? Because if this is the other parameter, it means that the superposition of all the possibilities is trivial. So it means that in a single instant of time, I can have one particle plus, I mean, it's the same but different, possibly 1 or 2, n times, and this has to be 0. But there is an issue here that if this sum is 0, it means that some particle numbers have to be negative. And then how do you interpret that? So my interpretation is that when the Hawking interpreted the spectrum of radiation, like the vacuum is created in pairs permanently, then the black hole takes one of the pairs and the other disappear. So from my mind, it comes out that probably, of course, the black hole not only, and it's logical, it not only particles, but also antiparticles. And then when there is emission of antiparticles, probably there is recovery of information. This is the interpretation I do. And of course, when you sum all the possibilities, this gives you a trivial vacuum. You recover the trivial vacuum state, which is before the formation of the black hole. So this is more or less how I was able to connect. And why this is connected with Jan Baxter? Because, of course, if we continue studying deeply, these results, if there is a spontaneous symmetry weaken, there should be Nambu-Goldstone bosons. But so there are some holographic arguments that propose what's the relation between the entropy and the number of Nambu-Goldstone bosons, which I have not done yet, but these ideas have been proposed also. And where are those Nambu-Goldstone bosons? Of course, it's not a cinema. They don't live in the horizon. So it's just, if you analyze a little bit, in the Mexican hat, for example, when you are here, and this is for closing, the Mexican hat, which is this, the Nambu-Goldstone bosons, they are moving along the degenerate ground state because they don't need energy for moving. So they are changing vacuum permanently. So in the case of black holes, the similar interpretation is simply a Nambu-Goldstone boson would be a way to represent the swimming or the change of one vacuum to the next, but as long as you keep the same mass, the same charge, and the same angular momentum. Because there are many different ways where you can create a black hole with the same mass, charge, and angular momentum, and those different ways are defined by the entropy of the black hole, which is the amount of information which the black hole stores inside, which is proportional to the area of the event horizon, as Wittgenstein demonstrates. So that's why these two results might be connected, and of course, there are many issues in process and so on. And this is more or less what I wanted to talk about. And
Thanks. Questions, comments? Yeah. I have a question because I remember that the Goldstone theorem, when there is equality of broken generators and numbers in boson.
Yeah.
That result depends on what I like on the origin.
What is invariant?
Lorentz invariant.
Lorentz invariant, yeah.
So in the proof of the equality of these two, that is point where you use Lorentz invariant.
That's correct. Yeah.
But you are not mentioning it here explicitly, and I now struggle to remember when is the point.
That's very important. That's very important.
Somehow.
Yeah, that's very important because of course, in relativistic theories, the Nambu-Goldstone theory is respected. Yeah. So the Lorentz, the explicit.
But I would say like in Lorentz invariant theory, because relativistic energy doesn't need to be Lorentz invariant. Like for instance, in cover superconductor, they are like relativistic in the sense of high energy, but they are also like there is this animals counting. Maybe there. So
you mean in QCD? Okay. Yeah, that's very important. Yeah, what you say. Well, let's talk in the right language. Lorentz invariance. Yeah, you're right. I mean, the Nambu-Goldstone theory is valid when there is explicit Lorentz invariance. But when there is no explicit Lorentz invariance, is where the Nambu-Goldstone theory, it doesn't fail. What I'm saying here is because it doesn't fail. What happens is that two Nambu-Goldstone bosons, they merge in a single degree of freedom. So it means two broken symmetries. Now the relation is 2 to 1. Two broken symmetries give you only one Nambu-Goldstone boson. And it gives you a quadratic dispersion relation. And this, when I use the quantum Yang-Baxter results, I could factorize the phases and analyze how they go to zero, how the variables go to zero. If they go to zero linearly or quadratic at the lowest order. And I found that the momentum goes quadratically. And this case, this doesn't appear when it's a split, when there is a explicit Lorentz invariance. I cannot factorize all the triangles because these two guys cannot be factorized. This will be the end of the calculation. And when I try to group all the phases, I will see that the energy and the momentum go to zero both of them linearly, which is consistent with the Lorentz invariance case. No? So I mean, well, I didn't mention explicitly is because I consider this probably more fundamental, but and this case cover both Lorentz invariant and non-Lorentz invariance cases. And I think now that you mentioned QCD, these tools, this way to analyze the phase transitions, spontaneous symmetry breaking, and so on, could be applied to those QCD cases which you have mentioned. Which actually, in many cases, you can construct the R matrices, and those are particular cases which I am planning to follow up also.
Because in this particle physics cases, this Lorentz invariant broken, I think that is crucial. The point that there exists vacuum expectation value based Lorentz index. It means like Lorentz violating vacuum expectation value. Yeah. And then, which is not the case in Lorentz invariant. Then their vectors have zero vacuum expectation.
Yeah, but those violations are explicit. Even the Lagrangian violates the Lorentz symmetry in that case, no?
Right.
Then, of course, it's different to the spontaneous
let's say
symmetry breaking case. No?
But there is still like some vector which has value non-zero.
Okay. What you mean is as a consequence of the Lorentz violation, naturally there will be some vectors that
should be visible in the proof of the Goldstone method, of the Goldstone theorem, and of these anomalous counting.
Yeah. Well, more or less, I think I understand what you're trying to say.
And I think if I remember correctly, but I'm not sure because that's why I'm asking.
Okay, continue.
I think that there is actually working maybe play it to target that you may have vacuum expectation value non-zero for zero component of some current. And J0 of some important number would have non-zero vacuum expectation value, right? Is it possible only in Lorentz non-invariant system because otherwise you to have a zero, and then you can substitute this J0 for a commutator of other Q K0.
Mhm.
You know, similar thing what you did.
The first demonstration, now with the two, without including the double commutator, yes.
So you will study like a vacuum expectation value of a commutator of two currents. And then and these two are coupled to the same Goldstone boson. And this I think is the original proof of this with two generators gives to one Goldstone boson.
Okay. Do you have the paper, the reference?
I think Nielsen China.
Nielsen China. Okay, Nielsen China. Yeah, I read those papers, but
China, I think they were the first.
They were the first guys who noticed the problem, and they developed the. Actually, no, even Nambu noticed the problem. Chiro Nambu.
They provided theorem for.
Yeah, but they were focusing the content. Nambu just cared the dispersion relation, and then.
But they showed also.
Yeah, exactly. And then after.
Line of cosine.
They also did this. Okay.
But then what you are showing here is actually that you consider double
Commutator because it's the only way how the quantum Jambaster equations emerge. That part Nielsen and Chao didn't do. But that's the part which Nielsen and Chao didn't do. And Murayama, Watanabe, and Browner that work at the project. Murayama, who is in Berkeley now, probably almost retired. But he was director of IPMU for long. That's how I knew about the problem, because I was in Japan for that period, and in Tokyo particularly. Then I knew about that problem, then I started to. But then the novelty of this is the fact that the Nambu-Goldstone theorem is a consequence of quantum Jambaster equations. And because the way how the Nambu-Goldstones interact obey these relations. And of course, at the infrared level, there's no creation of destruction of particles. So technically, you could say that this argument, which string theories lie, integrability, or these kind of issues could be applied also. Well, there is no creation of particles of this kind of thing. Debate the answers and this kind of issues. Yeah.
The question: if you do your construction of double commutators, don't you need three generators?
What?
Three generators. Because this commutator which you put there. Both of.
Yeah, they will generate another one. The commutator will give you. Yeah, at least.
Substitute for the commutator, you can substitute the third generator.
Yeah, of course.
If you want both of them give non-zero.
Yeah, exactly. You need at least three broken generators, yeah, in this case. At least. Yeah, that's right. Well, of course, there might be, what your point probably is that there might be cases where there are a lower number of generators and still you got quadratic dispersion relation.
Nielsen China said that there is a lower limit on Goldstone bosons, that there should be less than half of the generator.
Yeah, what happens is that it's not that the generators, I mean, the argument here is not that the generators are less. It's simply, well, what this other guy says that there are some symmetries which are redundant, that they give you the same. But what I'm saying here is that the Nambu-Goldstone theorem still is obeyed. There are these two broken generators, which you can say that they are redundant symmetries, whatever. They give you each one Nambu-Goldstone, but these 2 degrees of freedom merge, they fuse in a single one, such as the Cooper pairs, more or less. And they, of course, the dispersion relation effectively change from the linear. When they merge and they fuse, the dispersion relations becomes quadratic. This is more or less the point of view here. Because in this I know they did with the content, but of course they never introduced Jambaster or not even double commutator. Yeah, well, the double commutator, of course, this at the end, the summary is these 4 triangles. At the end, is just the vacuum expectation value of the other parameter. At the end, finish being, because this is after everything can be simplified to the vacuum expectation value of the other parameter. which is non-zero, which is the part of your